Hello everyone, this is Dilip Chakravarti, Assistant Professor in Cybersecurity Department in Institute of Aeronautical Engineering. Today we are going to discuss about BTrees. Okay, BTrees are very important in data structures. So in the earlier classes we discussed about binary search trees, and AVL trees. Let's see about B trees. Okay, so the minimum thing you require to know about B trees before learning about this B trees, you should know about MV trees. Okay, MV search trees. What is an MV search tree? An MV or a multi-way tree is a tree that has the following properties. It follows some properties. We say it as a MV search tree. Each node in a tree can have at most m children. Okay, at most m children will be there. Suppose if you are considering a four-way tree, so each node will have at most four children. That means it may be 0, 1, 2, uh, or 3 of 4. Okay, maximum of 4. Okay, nodes in the tree have at most m minus 1 key fields. So there are m minus 1 key fields. So suppose if we consider in this example, this is a four-way tree, so where it will have a maximum of 4 children. Okay, and the keys, if you see the keys, so it will be maximum of m minus 1. That means 4 minus 1, so maximum of three key fields will be there. Okay, and pointer references to the children. So this is a four-way tree, four-way search tree. So there is a procedure involved. We'll see that procedure how we are constructing a M-way search tree. So observe here, these are the keys K1, K2, K3. So here, this left subtree of this K1, and this one is the right subtree of K1. Okay, it is in between K1 and K2. So this tree is in between K2 and K3, and this one is um, right for K3. Okay, what are the values? What are the elements we are going to place here? Means all the keys which are less than K1, all the keys which are less than K1. Here I am going to place all the keys which are greater than K1 and less than K2. Okay. Similarly, here greater than K2 and less than K3. Here all the values are greater than K3. Okay. So if you observe this example, you'll get a clear idea here. So here all the values are less than 50. Okay, 1930. So here it is greater than 50 and less than 60. Okay, observe here 58 and 59 are greater than 50 and less than 60. So here greater than 60 and less than 80. Okay, here greater than 80. Okay, in this way we are going to construct a M-way search tree. Okay, so observe this example, another example. It is a four-way tree where it consists of at most four children, and the key fields are 4 minus 1, that is 3. Okay, so here it will be less than 50. Okay, all the elements here we are placing are less than 50, and here the elements are greater than 50 and less than 100. Okay, here greater than 100 and less than 150. Okay, here greater than 150. Okay, so in this way we are going to place the elements. Okay, so here observe for these nodes also we are placing the same, we are following the same procedure. So all here are less than 85, and here greater than 85 and less than 95. Okay, so we are placing like that. Okay, okay. uh, yeah, similarly observe here for this node all the elements are less than this 125. Okay, 110 and 120. So this one four-way search. So An MBA search tree is more constrained MBA tree, and these constraints mainly apply to the key fields and the value in them. Okay, so we are following some conditions here. We are following some constraints here. So how will be my M basis? Okay, each node in the tree can associate with M children. Okay, it can associate with M children, and how many keys? As I already told you, it must have maximum of M minus one key fields. Okay, the keys in any node of the tree are arranged in sorted order in ascending. The keys in the first k children are less than the kth key of this node. Similarly, the keys in the last m minus k children are higher than the kth key. Okay, so we have seen pictorial representation of M-based search tree. So this is another example for M-based search tree where we are placing the elements. It is a three-way search tree. It consists of three children, at most three children, and the key fields are 3 minus 1, that is 2. Okay, so 11, 40 are key fields. Left to that 11, we are placing the all the elements that are less than 11, and right to 40, all the elements that are greater than 40. In between, I am placing the elements which are in between 11 and 40. Okay, so now let's discuss about this BTrees. BTree is an extension of MV search tree. It is an extension. It looks similar to MV search tree. Okay. Besides having all the properties of an MV search tree, BTrees was developed in the year 1972. So they are developed in the year 1972 by Bayer and McCreight with the name height balance M-based searches. So first earlier it was named as height balanced M-based searches, and later it was changed to BTrees. Okay, it has some properties of its own. There are some properties for BTrees. All the leaf nodes in B-tree are at the same level. All the leaf nodes will be at the same level. All internal nodes must have m by 2 children. Suppose if you are saying it as a 4 order of 4, then 2 4 by 2, that means two children are there for internal nodes. If the root node is a non-leaf node, then it must have at least two children. Okay, so this is one condition. All nodes except the root node must have at least m by 2 minus 1 keys and at most m minus 1 keys. So I can take m by 2 minus 1 keys other than for root node, and I can take a maximum of m minus 1 keys. Okay, so we'll see with an example, you get a clear idea about it. All the key values in a node must be in ascending order. Okay, so whatever the keys we are taking, those will be in ascending order. So observe this B tree with the order 4. Okay, so order 4 means maximum of three keys can be allowed. So maximum of three key values in node and maximum of four children. Okay, so observe here, I have taken a tree 30 70. First root node is 30 70. So here all the elements are that are less than the 30 will be placed here. Okay, so all the elements that are greater than 70 will be placed here. All the elements that are in between 30 and 70 are placed here. Okay, so here also I have taken the children. See, observe here, all the leaf nodes are at the same level. Okay, so we are following these steps. We need to consider these conditions. So, what are the operations we are going to perform on BTrees? The following operations are performed on BTrees. So, it may be search operation, insertion operation, and deletion operation. Okay. So the search operation is performed as follows. We are going to perform the search like this. Read the search element from the user. We are finding the element, what element to search. Compare the search element with the first key value of the root node. Okay. If both are matched, then display the given node. Okay. If that value itself is what we are searching, we are displaying it as given node is found. Otherwise, If both are not matched, then check whether such element is smaller or larger than that key value. If search element is smaller, then continue the search process in the left subtree. Okay, so we'll be seeing in the left subtree. If the search element is larger, then compare the search element with the next key value. Okay, in the same node and repeat the steps. We are going to repeat that same steps 3, 4, 5, and 6 until we find exact match. Okay, if the last key value is leaf node is also not matched. So if you have checked all the keys, including the leaf node, so if it is not matched, then you need to display it as element not found. Okay, just you are terminating the function. Observe here, you are searching for an element 120. So first I go to the root node. As 120 is greater than 100, I'll move to the right side. So here I found 130 and 80. So I'm comparing with this element. 120 is less than 130. I'll move to the left side. Okay. So here 110 and 120. So here I found the element in the leaf node. I'm just displaying it as successful. Okay. I have given it in step by step. You just see this. So in the first step, I'm just comparing with my root node. Okay. In the second step, I move to the this side. As 120 is greater than 100, I move to this side. In third step, I move to the this side. Okay. So now we got the key having value 120. Okay. So now let's see about the insertion operation BTrees. How we are going to insert. Okay, it is also same like all the insertions we have seen earlier. In a B tree, a new element must be added only at the leaf node. Okay, we are adding it as the leaf node. That means the new key value is always attached to the leaf node. Okay, the insertion operation is performed as follows. Check whether the tree is empty. First of all, I need to check whether tree is empty. If tree is empty, then create a new node with new key value. So I need to create a new node with new key value and insert it into the tree as a root node. So I'm trying to insert it as a root node. Why? Because as the tree is empty. If it is not empty, if tree is already existed, okay, if tree is there, then find the suitable leaf to which a new key value is added. Where I need to insert, I need to find by using the binary search tree logic. Okay, if the leaf node has empty position, add the new key value to the leaf node in the ascending order of the key value. Okay, if that leaf node is already full, okay, if that is already full, what we need to do is we will split the leaf node by sending the middle value to its parent node. Okay, we'll split the leaf node. Okay, we are going to repeat the same procedure. If splitting is performed at root node, then middle value becomes the new root node. Okay, if you are trying to split at the root node, then middle value will become the root node. Okay, we will see with an example. I will get a clear idea about here. uh, Consider the pictorial representation shown below. So if you observe here, this is a B tree of order 5. Okay, so now I'm trying to construct a B tree of order 5. I'm trying to insert a key 9. Okay, I'll come to this position. 9 is less than, I'll be moving here. Here 29, I need to go to here. Okay, so here already there are 4 elements, 1, 2, 3, 4. So B tree of order 5 means I can take 5 minus 1, 4 keys, but already it is full. So now I need to insert 9. If I insert 9, it becomes 5 elements. So at that time, what I will do? So as we have seen, we need to split the node. We need to split this node and we'll be sending one node, one element to the upward. Okay. So we'll split it as the violation came, as the violation of rule came. So we just split it. So observe here 3, 4, 11, 27. Now 9 is sent to upwards. Now the tree becomes 9, 20, 9, 23. Okay, it looks like this. So construct a binary, construct a B tree of order 3 by inserting numbers from 1 to 10. Let's see with an example. Uh, let's see with an example. Okay. Uh, construct B tree of order 3. Okay, let's see with an example. First, we'll take 1. So 1 is taken as my first node. Insert 2. I'll be taking 2. As order 3, I can take up to 2 keys. Okay. So then while inserting 3, I can't insert 3. Why? Because the order is 3. So I can't place in that one. So I'll just split my node. Okay. Now it becomes like this. So middle, as we have seen the condition, if it is the root element, I'll make my middle element as a root. Okay, 2 comes here and 1, 3. So then I'll be inserting simply 4. No problem there. So as there is space, I have included. Okay. Now then, if I'm trying to insert 5, so already it is full. 2 elements are already there. What I will be doing? I'll be just inserting and I'll be pushing my middle element upwards. Now it becomes 2, 4 here, 3 comes here, and 5 comes here. Okay. So then element 6. So as 6 is greater than 4, I'm just simply inserting here. Okay. So when you get 7 again, so here it's a violation there. Okay. So you observe here. Then you get 6, 7. You'll get a violation there. So you'll be sending 6 to upwards. But already here it is full. So again you need to send the middle one upwards. That means 4 should come here. So for left side you'll be getting 2, and for right side you'll be getting 6. Okay. In this way you'll be inserting the element 7. Now insert 8. There is no problem. We can directly insert 8. So there is space. Now if you are trying to insert 9, so again there is a problem. So already full. I'll be sending my 8 here. 6, 8, 8 will come 10 here. Okay. So 6, 8, I got 10. So in this way, I'm going to insert my elements. I'm going to construct my B tree of order 3. Okay. So then deletion. How we are going to delete a key in a B tree? It includes two cases now. Okay, there are two cases: deletion of key from a leaf node, whether I am deleting an element from leaf node or whether I am deleting an element from internal node. Okay, so there are two cases. We will see one by one. In the first case, deletion of key from a leaf node. Okay, if I am trying to delete it from my a leaf node. So if you want to delete a key that is present in leaf node of B tree, then we have two cases possible. Again, there also we are having two cases. If the node that contains the key that we want to delete in turn contains more than minimum number of keys. Suppose if you are trying to delete that key, if it becomes a minimum number of keys, okay, it is violating the rule. So then what we need to do is, then we can split the delete. We can simply delete the key. So if it is not violating the rule, we can simply delete the key. Okay. See here, consider the pictorial representation. Say we want to delete 64. So 64 here, no problem here. Already elements are there. We can simply delete it. So there is no violation of rule here. Okay. So minimum we are having the elements 65 and 68. No problem. We have deleted that element. Okay. So if the node that contains the key that we want to delete in turn contains the minimum number. Suppose if there are minimum number, if you delete that, if it becomes a minimum number, so then there are three cases possible. So one is, in order to delete this key from B-tree, we can borrow a key from the immediate left node. Okay, so I can get it from the immediate left node, or I can get it from the immediate right node. Okay, so we can say them as siblings. So left sibling or a right sibling. The process is that we move the uh, uh, we move the highest value key from left sibling to the parent. Okay, or we can move the lowest value from a right sibling. Okay, so we can replace like that. Okay, so last case would be that neither the left sibling or right sibling are in a state to give the correct node. Suppose from left sibling or right sibling, if you are trying to borrow the element which causes minimum in that node. Okay, minimum keys in that node. So at that time, what we'll do is we'll merge the two nodes. Okay, so we'll do a merge with either one of them. Okay, we'll see them. Consider the case one. If you are trying to delete 23, so where is 23 available? I'll go to here and here. If you observe, if I delete 23, only it becomes one node 27. Okay, so which is violation. So only one node will be there. So for that, what we'll do is we'll borrow from the left sibling or right sibling. So it is not having left sibling, so simply it is not having right sibling, simply we'll get it from the left sibling. Okay, so I'll get 16 here. Okay, so now it becomes 16, 23, 27. So the middle one will be sent to upwards. So yeah, not middle one. The least one in the right supply is sent to upwards. So that means 16 is sent to upwards and 20 comes here. Okay, 20, 27. I hope it is clear. So simply if you are deleting 23, so what happens? Only one node will be there, 27 will be there. Okay, at that time what we'll do is we'll be picking the element from the left subtree or left sibling. So there I am picking 16. So 16 and 27. Okay, 16, 20 and 27. So I'll be sending the 16 to upwards. Now 20 comes here. Okay, it will be like this. This is my case one. So in the case two, we'll be getting from right subtree. Okay, observe here. If I'm trying to delete 72, if you are trying to delete 72, so here only 73 will be there. So then I will get it from another no, okay, another sibling. So maybe I'm getting it from this one. Okay, so here I'll get 77. So 77, 75, 73. So in this one, whichever is the biggest one, I'll be sending that one up. That means 77 will goes to upward. 77 will goes to upward and 75 comes here. So now it becomes 73 and 75. Okay, this is case 2. So case three, as I said, if it violates both the cases. Now observe, suppose if you are trying to delete 65, so then here you'll get only one node. So at the time, if you are trying to borrow from other, so there it becomes only one. If you are borrow from this side, there also it becomes only one. So then what we need to do? So we need to merge the nodes. Okay. So here we'll be merging the these nodes. So 51, 52, and 68. Okay. So I'll be getting this 60 downwards. Okay. So this happened after deletion. Okay. So I hope it is clear. Thank you. This is about BTrees. Okay.